everyone, welcome back. In this particular video, we will be discussing the problem matrix multiplication. What we are given is two matrices, grid 1 and grid 2. These are the variable names of those two matrices. You must multiply the matrices and return the result. Just simply two matrices are given of different dimensions, you can assume, because as you can see in the parameters, first matrix is having dimensions n1 comma m1. Second matrix is having dimensions n2 comma m2. So matrices will have different dimensions. You have to multiply them and then result will be also a matrix which you have to return. For matrix multiplication, if you don't know how it works, you can also refer to this article. However, we will also be discussing that how actually it works during this dry run. A very important note is a matrix multiplication logic will only work if the number of columns in the first matrix will be equal to the number of rows in the second matrix. If it is true, then only matrix multiplication is possible, otherwise not. So it is given in the question that always this thing will be true. That is always columns in first matrix, which is nothing but M1, will be equal to rows in the second matrix, which is nothing but N2. So it is always given M1 equal to N2 means matrix multiplication is possible. You don't have to think of a corner scenario where matrix multiplication is not possible. But let's see how actually matrix multiplication works. Let's take two matrices. First matrix having, let's say, 3 number of rows and 2 number of columns. Let's have first matrix having 3 rows, 2 columns. This is the first matrix. And let's have the second matrix, which is having maybe 2 rows but 4 columns. This is the second matrix. 2 rows but 4 columns. So let me just quickly create both these matrices. The first matrix dimension is, actually I have written something different. What we wanted was 3 rows, 2 columns. So this is actually 3 rows, 2 columns. And the second matrix is 4 columns but 2 rows, that is 2 cross 4. This is nothing but n1, number of rows in first matrix, number of columns in first matrix, number of rows in second matrix, number of columns in second matrix. And is the matrix multiplication of a comma b possible? If this is a, this is b. Answer is yes. Why? Because number of columns in first one is equal to number of rows in second one. What will be the dimensions of the resultant if input is having different dimensions? The matrices A and B are having different rows and columns. Output will be saying what? Output will be saying, I will take the number of rows from the first matrix. It is important that are you doing A into B or B into A? The answer will be different. And it might be possible that if A into B is possible, if you are able to multiply A with B, it is not likely that you will also be able to multiply B with A. You will have to check. Right now, C will be A cross B, that is A multiplied with B. So A will be taking, or you can say C will be taking the rows from the A matrix, from the first matrix. That is, it will be having 3 number of rows, and columns will actually be taken from the B matrix, which is actually 4 number of columns. So what will be the dimensions of output matrix? It will be 3 cross 4, where 3 is taken from A and 4 is taken from columns of B. So let me just quickly put values in these two matrices. This is 1, this is 2, this is 3, this is 4, this is 5, this is 6. And let's just say this is maybe 7, 8, 9, 10, 11, 12, 13, 14. We have just inserted random values. The values does not matter. Now let me just quickly draw the output matrix dimension. So what will be the dimension of output? 3 cross 4 means 3 rows, 4 columns. So let me just quickly have 3 horizontal levels and 4 vertical levels. This is 3 cross 4 for output. How will we use this information that we have to have the number of columns in first equal to the number of rows in second? We can't simply say that the multiplication will happen only with one cell. That is, it is not like 1 into 7 will come here, 2 into 8 will come here, and so on. No. What we are going to do rather is multiply the row from first matrix, each row from first matrix to each column of the second matrix. Each row of first matrix to each column of second matrix. Each row of first matrix to each column of second matrix. That is, if you will first pick this row, it will get multiplied with this column, then this column, then this column, then this column, one by one. Similarly, the R1 row of A will get multiplied with C0, then C1, then C2, then C3 of B matrix. Let me just quickly give the numbers. This is R0, this is R1, this is R2 for first matrix. There are only two columns, C0, C1. But here there are four columns, 0, 1, 2, 3, only two rows, R0, R1. And let's also give numbers for output. Now let's start by how these values will get populated. Then we will discuss actually the approach. Values will be, first of all, we talk about R0, C0. It will be the multiplication of the zeroth row from A into the zeroth column of B. R0, C0 means row will be taken by the first matrix, column will be taken by the second matrix, and multiply the corresponding values. What do you mean by corresponding values? You will say 1 will be multiplied with 7 plus 2 will be multiplied with 11. So output here will be 1 times 2 plus 1, actually 1 times 7, not 1 times 2, plus 2 times 11. Next, this value, how will it come? It will be coming from R0 of the first matrix multiplied with C1 of the second matrix. That is 1 times 8 plus 2 times 12. So let me just quickly write the value. It will be 1 times 8 plus 2 times 12. Each value in the first row will get multiplied with each column value in the second matrix. How will the R0 C2 come? It will be R0 from first matrix, C2 from second. That is 1 times 9 plus 2 times 13. 1 times 9 plus 2 times 13. And finally, R0 C3, it will be 1 times 10 plus 2 times 14. 1 times 10 plus 2 times 14. Obviously, I will not write all these values, but just let's quickly do a try run for some of those values. If we will want to calculate R1 C0 of the output, it will be multiplication of R1 from first, C0 from second. That is 3 times 7 added with 4 times 11. 3 times 7 added with 4 times 11. The point is, how will you calculate any random cell? First thing, in order to calculate any one cell of the output, do we have a single operation or a constant operation? The answer is no. It is requiring a loop over the columns of the second matrix or the rows of the first matrix. That is, we are running a loop over this, and multiplying the corresponding values. Not for R2, C2, but if I take R2, C2 itself, it will be R2 from first, C2 from second, multiplying the corresponding values. 5 into 9 plus 6 into 13. So in order to run a loop parallelly, not one after the other or not one inside another, it will be parallelly happening. A loop over R2, a loop over C2 happening together. One by one, we will be updating values. That is going to the next column, next row. So one loop will be required to calculate each element of the output. But how many elements are there in output? There will be 3 cross 4 elements. So how many total loops are we going to require in order to form the output matrix? We will be requiring, first of all, a loop over all the cells of output. That is 3 times 4 time complexity will be there to go to each and every cell. And then to calculate each cell value, we are running a loop over 2 times. That is over 2 columns or 2 rows simultaneously. That is nothing but multiplied with 2. Now, how to generalize this? What is this 3? This 3 is the number of rows of output. How are the number of rows coming? They are coming from the first matrix rows. That is the n1 value. How is 4 coming? 4 is coming from the columns of output. Where are they coming from? The first, actually not first, but the second matrix columns. That is M2. N1 times M2 times, where is 2 coming from? It is actually the common dimension. So either you can write M1 or you can write N2. Both are equal. Number of columns in first matrix are equal to number of rows in second matrix. 2 rows, 2 columns. You can use anything. Either you can use M1 or you can use N2. But the point is the time complexity will be cubic in nature. There will be 3 loops total which will be required, which are nested one inside another to form this output matrix. One loop over the rows of output, one loop over the columns of output, and the third loop to calculate the answer of each cell. And in order to calculate the output of each cell, we have to run a loop over rows of first matrix, columns of second matrix. So Let's just quickly see how actually we can find out the value of R2, C3. So when we say that we want to calculate the value of R2, C3, we have fixed R2, we have fixed C3. So what is getting fixed in the first dimension, in the first matrix? The R2 is getting fixed. R2 is getting fixed. So let's say this is R variable. Let's say this is C variable. So this is also R. And what is C3? C3 is coming from this. This is also C. Row will get fixed from first matrix, column will get fixed from second matrix, and we will correspondingly multiply. And since we have to add all those multiplications, we can assume initially this particular value is nothing but 0. What we will do is we will run a loop over columns of A or the rows of B simultaneously. You can just use a single variable to update both of them. Let's say we are using a variable known as K in order to do it. Okay? Or you can use anything apart from RC. So let's say we are using a variable K. What we will do is R comma K, where K initially will be 0. That is from first matrix row as 2, column as 0, take the value, which is nothing but 5. But from second matrix, take the K as the row, not the column. That is, row will be taken as 0. If K was 0, K will be 0 for row of the second matrix. That will be multiplied with, you can say, the value 10. That is, column will remain 3. So you are getting multiplied it with 10. If I generalize this value, how is your 5 coming from? You are saying it is nothing but your first matrix row is the same as the output row. Column is getting updated as K variable, first 0, then 1, and so on. Right now, it is only getting updated from 0 to 1. Multiplied with B matrix, row variable coming from K, because the loop over first matrix is on column, second matrix is on row. It is on column of the first matrix, row on the second matrix. That's why the dimension K is for the column of A, but the row on second. And what is the column index for B? The column index is fixed as the C variable, whatever your output column is. We wanted to calculate the value of R2, C3. That's why we are saying in the first matrix, R will remain 2. In the second matrix, column will remain 3. So R is fixed, C is fixed. Only what is changing is K, which is changing together for the first matrix column, second matrix row. And we will do it for all the K values, not just for K0, but for K1 also. That is, these two values will also get multiplied. So we will just multiply 6 times 14 and add it in the previous resultant. And this fashion, we will be able to find out all the values of each of these cells in the output. So overall, cubic time complexity. But what about the space complexity? If we talk about space, time is cubic, or you can say time is n1 times m2 times m1. So let me just write it again. What about space? We can say space is nothing but only quadratic. The reason being, we are only creating a matrix, which is a 2D array. And 2D array will take n into m, that is rows into columns number of cells. So space complexity for output data structure will be n square. However, there will be no extra space as such. This is the output data structure. These are input data structures. So if anyone asks you about extra space, that is constant in any programming language. If anyone asks you about the output data structure space, that will be quadratic. So right now, I'm just writing quadratic. In the bracket, I'm writing output data structure. That is the output matrix. Will be taking quadratic space. And in order to do multiplication, you will be requiring cubic time, 3 loops, 3 nested loops. Okay. So now that we know about the approach, let's just write the instruction manual. First thing, we will have to create output matrix, create a output matrix. Let's say the name is grid 3 because input are grid 1, grid 2. Let's say the output is grid 3, where the rows are equal to n1, that is taken from the first matrix rows. Columns are equal to the columns from second matrix, that is equal to m2. And for now, you can assume that m1 number of columns in first will be equal to n2 number of rows in second. And why do we need it? If you will just look carefully what we were doing, running a loop over columns of first over rows of second. So if they are not equal, columns in first matrix are, let's say, 3, then you will not be able to multiply simultaneous values. Let's say there was another column in the first matrix. You can multiply 5 with 10, you can multiply 6 with 14, but there will nothing be multiplication for this particular cell with any cell in the second matrix. That's why number of columns in first should be equal to number of rows in second. Then only matrix multiplication is possible. Otherwise, you can't multiply those two matrices. So you can assume it is a valid scenario always. Creating output matrix, initially every value will be 0 by default because it will be a matrix of integers, and integers default value is 0 in all the languages. Now we have to start the logic, and how to start the logic is run three nested loops. First loop simply on rows. Run a loop over row index row r from 0 till the number of rows till n1, because in output there are total n1 rows, and actually row index will be from 0 to n1 minus 1. Last index will be n1 minus 1. Then inside that you can run a loop over the columns variable. That is, you will require two loops, two in order to go to each and every cell of output. It is just like traversing over a matrix. So now you will be requiring column loop from 0 to n2 minus 1. But now you will be requiring a third loop to calculate each cell's value, that will run over the first matrix A matrix rows, sorry, columns, and the second matrix rows. That is, together first matrix and second matrix will iterate, and we will be able to calculate the corresponding pair to multiply. So run a loop over, let's say, variable k from 0 only till what? Till the common dimensions, that is till m1 or till n2. And obviously, since we are starting from 0, we only have to go till m1 minus 1. If the common dimension was having size 2, we have to run the loop from 0 to 2 minus 1, that is 0 to 1. Only two elements are there. Two elements are there. How to calculate the pair which we need to add in the output? We will add the pair which is from first matrix, from A matrix, that is grid 1 matrix, the same row but column will be the common dimension, that is k, multiplied with grid 2's common dimension will become the row this time, and the fixed dimension will be the column, which is c. Add this pair in the output, and what will be the output? In the output, which is nothing but grid 3 of r comma c. We are every time iterating over each cell of output. That is, row will become 0, 1, 2, 3, column will become 0, 1, 2, 3, whatever number of rows and columns are there. And we will just add all those multiplication pairs in the output. That is, if there are two pairs, we will just keep on adding those two pairs for each cell, those two pairs for each cell. And this is how we will form the entire matrix. That is what we are doing right now. So this third loop is just to calculate all those pairs and add them in the corresponding cell. Finally, after all these three nested loops, we will be able to say that the entire code is done. We can return happily the output matrix. It is completely populated. So we can just say return the output matrix, return output, which is grid 3, whatever name you have used. So code will be pretty much short, provided that no corner scenarios are given. That is, provided that no such scenario where matrix multiplication is not possible is given. However, I will strongly suggest you to do some problems where there might be even more corner cases added. That is, try to think where you will add that condition and what condition will you add in order to check the corner scenario. We have already discussed the approach in order to solve this, and also written the instruction manual, which will be requiring three nested loops, because the output multiplication, the output matrix, is not just simply multiplying the first matrix cell with second matrix cell. It will require a loop of pairs to get multiplied and added. Let's start with the matrix creation first of all, and I will be coding in this current video in Java programming language. So what we have to do is create output having name grid 3 of the rows being taken from first matrix, that is n1, columns being taken from second matrix, that is m2. And initially you can assume each cell's value will be 0 because integer's default value in Java is 0. Now we have to run three loops. First loop over the rows, second loop over the columns, just like you run it over a matrix. So I'm just for now marking question marks. I'm just having initialization and termination with a question mark. For columns also, you will start from some value, you will end at some value. But for calculating each cell, you require a third loop, which will run simultaneously or concurrently over the columns of first matrix, over the rows of second matrix. If I just show you, it was running over columns of first matrix C0, C1 and rows of second matrix R0, R1 simultaneously together, and we were getting pairs from them. So let's have the common dimension with the name K, which is starting from some value again, going till some value, and every time incrementing. Now the point is, how will you find these quotient marks? Finally, you will obviously have to return the grid 3, that is output. But let's first discuss the row quotient marks. How are we iterating over rows? We are going from row 0 till row 2 if the output is having 3 rows. That is, whatever the output number of rows are, go to each and every row from 0 to number of rows minus 1. So since output is having n1 rows, we will go to starting from 0 row going till n1 minus 1, or you can say less than n1 each row. What about columns? We will start from 0th column only and go till the last column. So given a matrix having 4 columns, we will go to third index column. And where is 4 coming from? This is m2, or you can say this is coming from this variable. We will say run the loop till m1, or not m1 but rather m2 minus 1. That is the last index will be number of columns minus 1. What about the common dimension? Common dimension will also start from 0, but it will go till the number of common elements. That is, number of columns in the first matrix or number of rows in the second matrix. That was common among them. 2 and 2 was common. So either you can take m1 or you can take n2. Both are equivalent. It will be correct using any of those two variables. So for now, I'm taking m1. And again, you have to just run the loop till less than m1. That is m1 minus 1 is the last index. How will you get all those pairs? You will say, in order to calculate the outputs, let's say R2, C3, R2 will remain fixed for first matrix, C3 will remain fixed for the second matrix in the pair. So what will be the pair? Pair will be, we will add that value in the grid at R, C, we will add the pair having the grid one's row fixed as the same row of what we want to calculate with some column multiplied with second matrix having the same column as the output, that is the same column C. Now, what about these two question marks? Both of those question marks are having same value. And what is those values? That is a common dimension. That is, we are running a loop over 5, 6, 10, 14 together and just multiplying correspondingly 5 with 10, 6 with 14. So we are running a loop over columns of first matrix using k variable and rows of the second matrix using the same k variable itself. So only 3 loops are required, not 4 loops. That's why if you will tell what is the time complexity of this code, usually using the code itself, you can easily say time complexity is n1 times m2 times m1, or essentially you can simply say cubic time complexity is there, n power 3 time complexity is there. What about the space complexity? If we talk about input, then of course there are two data structures, n1 into m1 plus n2 into m2. But when we talk about output, we are having a grid of n1 cross m2, which you can say in simpler terms is quadratic time complexity, not time but space complexity. So time was cubic due to 3 loops, but the space is only quadratic, the output space, the grid which you are about to return. But when we talk about the extra space usually don't consider the input data structures. That is, it will not consider grid 1, grid 2, and it also usually don't consider the output data structures, the extra space complexity. That is, we will also not discuss or include grid 3. So if all the 3 grids, if we want to exclude from extra space, what is the any other data structure? There are just 3 variables R, C, K, 4 bytes each usually, integer variables. We will say extra space is constant, no extra space. So extra space being constant, output space being quadratic, time being cubic. That is the time and space complexity analysis for the matrix multiplication. However, let's just run this code and confirm whether it is working without any compilation issues. Then we will also submit it and see whether it is working for any corner scenario possible or not. However, there will not be any corner scenarios where matrix multiplication is not possible. It will always be there. Always the matrix multiplication is possible, but it might be having values like 0 in the matrix. It might be negative values in the matrix. So in all those scenarios, our code is working, as you can see. That was the problem, matrix multiplication.